Hey, my name is Josh Fair. I'm currently taking Physics 2212 at Georgia Tech, and this is my lab video. This lab discusses magnetic braking with the Farad activity. So here we go. Introduction and models. So the purpose of this lab is to observe and collect data on a magnet falling through a tube and apply that data to Faraday's law. As you can see here, we'll be using 5 key concepts today. Faraday's law being the first with the formula on the side, the Biot-Savart law being the second with the formula on the side, the Ohm's law being the third with the formula on the side, and a magnetic force on a loop and Newton's third law being the fourth and fifth. As you can see on the right, there's a magnet, and this will relate to the aluminum tube that we'll be discussing later. Now the slide is exactly the same except for the model on the right. This model is what we're using during the experiment. The system is the aluminum tube and the magnet that's falling through, and the surroundings are, well, everything else around it. As you can see, the force of magnetic is pushing up against the magnet as it falls through, and the force of gravity is pushing down. This will be discussed later, so keep it in mind. Now these are the main result overview. We've calculated the measurements of the aluminum tube, the length, the width, the mu from the previous lab 3, and the magnet mass we calculated that as well. We found an average time from 5 key trials of the magnet dropping through the tube, and we compare that to the computational time that we will find for the glow script code that we will discuss later. So here we go. Experimental model. So the experiment was, like I said before, to drop a magnet through the aluminum tube and calculate the time it took. 5 trials total. We first did this by calculating the south and north pole of the magnetic tube, dropping a magnet through the tube 5 times and recording each time and determine the time taken to fall after. As you can see, 5 trials and the average time was calculated here. Now, why can't we use a ferrous tube, for example, steel type? Well, a ferrous tube contains iron, and iron, as you know, interferes with magnetic fields, and thus the data would be skewed. What happens to the magnet? How does this compare to magnetic falling in free space without a tube? Well, the magnet falls slower than in free space as there is a magnetic force here that is pushing up, as shown in the previous model on the second slide. Now, onto the computational model. So here are the initial conditions are listed here, here, and here. The initial bar has 0 velocity as it's dropped from rest. Now, this is the code used to create the tube in GlowScript, as you can see here. The measurements we discussed earlier are listed here. Here's the code to create the bar magnet in GlowScript, as you can see here. The measurements that we discussed earlier are again listed here, and the bar magnet is visualized as well. Here's a code to calculate magnetic flux and the magnetic field of the bar magnet. The formulas that we discussed earlier are used here, especially in key here in particular. And now moving on to the loop created in GlowScript. Faraday's law is used here as well to calculate magnetic flux as well. And again, the next part of the loop. So after that, this is the final GlowScript model that it gave us. This graph is slightly off as the magnet should slow down in the tube, which means it should not be linear. Now this is probably due to the mu from the previous lab being off, as it was slightly higher than it should have been, or probably some formula error in my code as well. So the intensity of coloring on the tube indicates the magnitude of current flowing through each wing. Red and blue indicate current flowing in opposite directions. So which color correlates to clockwise current and counterclockwise? Well, red corresponds to counterclockwise, and blue corresponds to clockwise. Now this is known using Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Well, nothing will happen. The direction of the current will flip, and that's all. How does the total time in tube with your real-world system compare to that of your computational system? How might the computational system be made more accurate? Well, real world is slower due to the effects of air resistance, but more accurate by adding bit. It can be made more accurate by adding bits into the code. And how does the shape of the velocity versus time plot tell you about the force acting on your bar magnet? Well, ideally, the slope of the graph should be curved, which means that the forces would be unequal. But in this situation, since it's straight, it wouldn't be equal. But correctly, it should be curved. So, discussion and conclusion. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, the induced current would be more significant, thus slowing the magnet even more, as the force of magnetic would increase, as shown in the bar graph before, it would go up. And what if the holes of slot were cut into the tube? How would this affect the ring currents of the model? Well, the current would be less, and the magnet would fall through faster. Thank you.